Hello and welcome to Sean White's Solar and Energy Storage Podcast. The title of this podcast is NEC Article 706, Energy Storage Systems, Part 3, through the end. I know in an previous podcast, I read Article 706, so this time we're not reading it, we are discussing it. We are bringing some sense to it. In this podcast, we will go over NEC Article 706, Energy Storage Systems, Part 3, Installation Requirements, Part 4, Circuit Requirements, Part 5, Flow Battery Energy Storage Systems, and Part 6, Other Energy Storage Technologies. To learn more about energy storage systems, go to solarsean.com. Hey folks, we're still covering Article 706, that's Energy Storage Systems. We've covered Part 1, General, which pretty much has generally most of the stuff there. Then we covered Part 2, Disconnecting Means, also known as DISCOs. Now Part 3, Installation Requirements. Then we're going to move on to Part 4, Circuit Requirements, which is pretty standard throughout the National Electrical Code for what you learn there. And then there is going to be Part 5, Flow Battery Energy Storage Systems. And last but least, because it's so short, is Other Energy Storage Technologies. Now let's get ourselves back to Part 3, and that is going to be Installation Requirements. Now we're talking general, and that is sort of like a category that they make when they don't know what else to call it. General. Maybe they should have called it Sergeant. Anyway, has A, B, C, C1, and C2 before we hit directory. Okay, Part 3, Installation Requirements, General 706-20A, Ventilation. So pretty much what this is saying is that you need to have ventilation that is appropriate for your energy storage technology. So one of the things that has happened in the past, especially before they had Article 706, is people were looking to Article 480 storage batteries, which was pretty much always used for lead acid batteries. And lead acid batteries, when you overcharge them, they can make hydrogen gas, which is very explosive. So they were always saying to have proper ventilation. However, when you charge a lithium battery, there's no danger of making hydrogen gas, so there's no reason to have ventilation. Just think of your cell phone in your pocket or your computer. We're not gassing off hydrogen from these lithium batteries. So in a way, they're safer. You can't build up some explosive gas from a lithium battery. So just make sure that it is appropriate for your energy storage technology, which means with lithium, skip it. And most people are doing lithium these days, so you can skip it. Now, dwelling units. And so 706.20b dwelling units, the exception is almost the rule. So is going for 1 and 2 family dwellings like most of the time. And so we shall not exceed 100 volts DC between conductors or to ground. Exception, where live parts are not accessible during routine maintenance, a maximum energy storage system voltage of 600 volts shall be permitted. So that's a big difference, 100 volts or 600 volts. So pretty much all the energy storage systems that you're buying include electronics, which means you're not going to do maintenance internal to that box. So for instance, if you're going to have one of these energy storage systems that we've been looking at and your live parts are hidden and you're not supposed to do maintenance on them, then the output of that energy storage system that includes an off switch can be up to 600 volts. So usually what we're looking at for dwelling units, 600 volts. So the exception is the rule. And you will notice that many of our energy storage systems go over 100 volts on the output, but some of them stay down to 48 volts, and then you can do maintenance on these conductors. Also, your equipment is going to be listed, and a lot of the listing will take care of this. So when you go buy what some people call a high voltage energy storage system, which is one that's not working around 48 volts most of the time, so we're going up over 100 volts at least, and most people don't even consider that high voltage, but the people selling the energy storage systems are calling it high voltage when it's under 600 volts because there's lots of different definitions of high voltage. Utility people that work on the utility lines call 600 volts low voltage. So once again, to clarify this, if you did have an energy storage system where routine maintenance of the energy storage system is going to be done, where you can expose yourself to those conductors, then those conductors would have to be under 100 volts. But if during routine maintenance we are not exposing ourselves to those conductors, then perhaps the output of that energy storage system can be up to 600 volts DC. A lot of times an energy storage system too doesn't even have DC on it. It'll be an AC output. Okay, so for the next thing on the general list, after dwelling units, we're going to talk about spaces around the energy storage system components. These are working spaces. This is so you have room to work on something. And just like with all things that you're doing with equipment in the National Electrical Code, you do 110.26. In fact, I think they almost don't even have to say this because it's just a given. Most people are going to be using the 110.26, which is for conditions under 1,000 volts. But if you were going higher voltage, then perhaps you would go 110.34, which is going to be for things that are over 1,000 volts. That's 1,001. Hey, what if you were at 1,000.5 volts? You wouldn't fit into any category. Haha. Then maybe you could have no space at all. No, that's not really the case. But hey, I'm always looking for little tricky exceptions. So as far as your energy storage system components, look for the manufacturer's instructions and listing. So you have to always follow the manufacturer's instructions and listings. That's part of the NEC. 706.21 means directory, and that means we have to identify our power sources. And then there's a couple of different ways of doing this, which is 706.21a, facilities with utility services and energy storage systems. So we're going to have plaques or directories. Pretty much what we're saying here is if you have a building with different power sources and somebody's going to turn off everything, either we're going to have to go to 705.10 or 712.10. So there's going to either be a plaque or directory if these power source disconnects are in different places. But if they're all in the same place, so multiple power sources shall be permitted to be identified as a group, then you don't need a plaque. So pretty much what we're saying, this goes throughout a lot of the renewable energy stuff because we're going to have different energy sources. If all the energy sources are in one place, then when somebody wants to turn it off, they're there, they turn them all off in that one place. If they're in different places, like in different sides of the building or inside the building, then at each one of these places, we're going to have a plaque or directory saying, hey, you turned this off, but there's other stuff on other sides of the building. And then there's going to be the standalone, which is B. And then also, we're going to pretty much have the same rules with standalone systems with that same exception. So it's pretty much the same language. And so just think about it. If you have multiple power sources and a firefighter comes, they want to turn everything off. They don't want to just go like, oh, I just turned it off, and then find out that there's another switch on the other side of the building that they didn't know about. Okay, so that's the end of part 3, installation requirements. And now we are on Roman numeral 4, circuit requirements. So circuit requirements are a lot of times used for something that's kind of advanced. It's wire sizing. But let's kind of try to see if we can take a very shallow look at this and not get overly advanced and confuse everybody. So it says circuit sizing and current, 706.30. That's under part 4 of Article 706, circuit requirements. First thing, circuit sizing and current. And then we're going to have a couple of different things there. We're going to have maximum rated current for specific current. That's 706.30A. Then there's going to be different conditions. So there's going to be A1, nameplate rated circuit current, A2, inverter output circuit current, A3, inverter input circuit current, A4, inverter utilization output circuit current, DC to DC converter output current. So we're going to just define what the current is. So nameplate rated circuit current first, that's 706.30A1. So this would just be on the nameplate of the energy storage system. And then 706.30A2 inverter output circuit current. So that would be your maximum current of the inverter output circuit shall be the inverter continuous output current rating. So if you're having an interactive circuit, that's like a grid-tied circuit, it's kind of usually just about the name of the inverter, like a 5 kilowatt inverter. But if we have an off-grid inverter output circuit, so that would be like standalone, then you would use the continuous current. Sometimes there's surge currents that are greater than continuous currents. In fact, most of the time there are with standalone inverter output circuits. So you're not going to use surge currents that go for short periods of time. We're looking for continuous output. And continuous in the National Electrical Code means 3 hours or more. Okay, now 706.30A3, and this is the inverter input circuit current. So we're talking about going, say, from batteries to inverter. And so remember that voltage times current is power. So the lower your voltage is, the higher your current has to be to get the same amount of power. And so what 70630A3 inverter input circuit current tells us is that the maximum current shall be the continuous inverter input current rating when the inverter is producing rated power at the lowest input voltage. So that's kind of counterintuitive. It's the lower voltage which is going to give you the higher current. And wire sizing is done based on current because current is what heats the wire up. Voltage, that'll cause a big spark, but current is what heats the wire up, and that's what we're talking about here. So your lower voltage is going to be your higher current for the inverter input circuit current. Okay, now we're defining currents at 706.30A4, and that's your inverter utilization output circuit current. Maximum current shall be the continuous AC output current rating of the inverter when the inverter is producing rated power. Pretty obvious there. Now, 706.30A5, DC to DC converter output current. DC to DC converter is pretty much like a transformer, but transformers only work for AC, and DC to DC converters work for DC. So you're going to convert higher voltage, lower current to lower voltage, higher current, or vice versa. And so what's the maximum output current of a DC to DC converter? It's what it says on the label. It's the maximum output continuous current rating. You can read that on the label of the data sheet. Now we are done with 706.30A. We're done defining currents. If you're used to solar systems in Article 690, this would be like the difference between 690.8A and 690.8B. Now we have 706.30A, 706.30B. So A tells us what our current is, and then B tells us about the required ampacity of the conductors. So let's kind of get into this a little bit. I'm just going to read this. 706.30B, conductor ampacity. The ampacity of the feeder circuit conductors from the energy storage system to the wiring system serving the loads to be serviced by the system shall not be less than the greater of 1. The nameplate rated circuit current determined in accordance with 706.30.A1 and 2. So that goes to A1 and 2 is the nameplate rated circuit current, or the inverter output circuit current was A2. And so we're talking about that. Or another way of doing it would be the rating of the energy storage system overcurrent protective device. So we have two different ways of doing it, and we're going to make sure that it's not less than the greater of. So we have two different pathways, and it's not less than the greater of, and A2 was the overcurrent protection device. So pretty much if we digested this deep enough, we would find out that this is pretty much the way that you do wire sizing throughout the National Electrical Code, and it's very complicated, and we have lots of different pathways. And I have found that probably 90% of the people doing wire sizing don't do it correctly, but they actually end up using a larger wire than it is required. And so this is the same wire sizing that I go over with in my book, PV and the NEC, which I should just call PV Energy Storage and the NEC. It's going to be pretty much the same answer that you're going to get when you do wire sizing. Okay, now the conductor ampacity of the grounded or neutral conductor. So a neutral, also called a grounded conductor, and it's covered here in 706.30C. And so we were already talking about that. That's a current carrying conductor that has the same voltage as ground. In the United States, it's a white wire, perhaps a gray wire in certain cases, and in other countries, it's usually a blue wire. So that neutral wire only has to be as big as the unbalanced current. So a neutral only carries unbalanced currents. So this is kind of a more advanced thing that somebody might be dealing with on a really large system, and they might want to try to save a little bit of money on their neutral by making that conductor a little bit smaller. Next, 706.31, overcurrent protection. And we're going to have 31A, 31B, 31C, D, E, F. And that's going to be it. Lots of stuff about overcurrent protection. And this is also kind of the same way that you do things throughout the code. So there's nothing different here, really. If you're doing overcurrent protection for your stove, for instance, it's the same type of thing. So what we have is 706.31A, circuits and equipment, and it pretty much just says that we have to follow the requirements for overcurrent protection which is also Article 240. And then it also says the requirements of 706.31b through F. And that's the next things that we're going to cover. And so that means that we're going to follow Article 240, which is a big article on overcurrent protection. So we're going to do it like our solar system, like a lot of things throughout the code, including a light bulb. Okay, next one, 706.31b, overcurrent device ampere rating, also known as amp, named Ampere after Mr. Ampere, who invented the amp. And then it's referring us back to Article 240, and it says that we shall have our overcurrent protection devices be not less than 125% of the maximum currents calculated in 706.30a. So we talked about that a little bit already because I referred back to there. And so we had 706.30a, and that was when we were defining our currents. And then we multiply times 1.25, and that's going to be our overcurrent protection device. However, there's this weird exception that actually nobody ever uses, whereas if you had an overcurrent protection device that's listed for 100% of its rating, then the ampere rating of the overcurrent device shall be permitted to be not less than maximum currents calculated in 706.30b. Nobody really does this. It's always there. It's kind of a waste of my breath to even talk about this exception. So isn't it funny how some exceptions are the rule that we were talking about earlier, and this exception never happens? So the reason that we have to oversize our overcurrent protection devices is because we don't want to have false trips. So let's say that it was a hot day and your overcurrent protection device was 100 amps and your current was 100 amps, your circuit breaker might pop. So we're going to size our overcurrent protection devices and our conductors to be at least 125% greater than these maximum currents, or shall I say maximum continuous currents, that we had from earlier on the page in 706.30a. Okay, now is only for direct current, and it says that 706.31c, direct current rating, overcurrent protective devices, fuses or circuit breakers used in any DC portion shall be listed for DC. And voltage, of course, obviously. Do we even have to say this? If you're going to have something that's DC, you have to use DC rated equipment. So it's more expensive and difficult to have a DC rated circuit breaker than it is for an AC rated circuit breaker, because AC goes off every time it cycles up and down. So if you have 60 hertz for the frequency of your grid, that means something is turning off or going to 0 volts 120 times a second. And if you have direct current, it's never going off, so it's more difficult to interrupt direct current. And so that's why direct current circuit breakers are unusual, and a lot of times people end up using fuses. 706.31d now, we got current limiting. A listed and labeled current limiting overcurrent protective device shall be installed adjacent to the energy storage system for each DC output circuit. So that's kind of what overcurrent protection devices do, is they are current limiting. Fuses. 706.31e is for fuses. Means shall be provided to disconnect any fuses associated with energy storage system equipment and components when the fuse is energized from both directions and is accessible to other than qualified persons. Switches, pullouts, or similar devices that are rated for the application shall be permitted to serve as a means to disconnect fuses from all sources of supply. So if you have an overcurrent protection device that's, say, between your battery and your PV array, it could get energized from both sides. So you need to be able to turn off both sides of that fuse so that you can pull the fuse out if it's accessible to people other than qualified persons. And for most of you that are working with an energy storage system, it's going to be some listed device that's going to have an off switch built into the energy storage system itself. So there's a good chance you're not going to have to worry about this, because if it is built into the energy storage system. But just beware that if you can energize something from both sides, you don't want just some Joe homeowner going down there and pulling out a fuse. Now, 706.31f, where circuits from the input or output terminals of energy storage components in an energy storage system pass through the wall, floor, or ceiling, overcurrent protection shall be provided at the energy storage component end of the circuit. So, by your energy storage system, you want to have overcurrent protection devices, and maybe that is built into the energy storage system itself. That would be nice. Now, on to 706.33 charge control. Yep, that's right. we are done with overcurrent protection and we're on to charge control. So that's just like it sounds, controlling the charge. So with charge control, we're going to have 706.33 charge control, 33A general, 33B diversion charge controller, which is going to include B1, sole means of regulating charging, B2, circuits with diversion charge controller and diversion load, B3, energy storage system using interactive inverters. Then we're going to look at 706.33C charge controllers and DC to DC converters, and that would bring us to the end of part 4 and on to part 5, which is flow batteries. So just hold your horses and then we will go with the flow. Okay, there we go. 706.33 charge control general. Provisions shall be provided to control the charging process of the energy storage system. All adjustable means for control of the charging process shall be accessible only to qualified persons. So we don't want some homeowner going in there, changing the charge control settings and blowing things up. Oftentimes, this charge control is going to be built into the energy storage system itself with some of your more modern lithium batteries. And we've looked over a lot of the different components. So just kind of think of this when you're thinking about those components that we've already looked over in this course. Okay, now there's something called a diversion charge controller, and we've talked about this a little bit before. And so that means your batteries are fully charged, or you're going through an absorption charge or some sort of slower charge where you're not giving it all you got. And you have this extra potential that you don't want to send to the battery. So what do you do with that extra energy? You could do nothing with it. And a lot of times we're talking about this in conjunction with a solar system. So it's a bright sunny day and your batteries are mostly charged up. What do you do with that extra energy? Do you turn off the solar array, slow down the solar array, or do you send that power to some other place? That is what a diversion charge controller is. And so we got some other topics underneath diversion charge controllers, which are B1, B2, B3. B1 is the sole means of regulating charging. The energy storage system employing a diversion charge controller as the sole means of regulating charging shall be equipped with a second independent means to prevent overcharging the storage device. So let's say that your diversion load is a pump. You're pumping water. What if your pump breaks? You don't want to overcharge the battery because your pump breaks, so you have to have some other way of controlling the charge, which might be, say, for instance, turning off your solar system in a different way. Okay, and now B2, which is circuits with diversion charge controller and diversion load. So we have a diversion charge controller and a diversion load, and you're going to have to comply with two of the following things here. So as we read the NEC 2, we would say 706.32 B21 and B22. So B21 is the current rating of the diversion load shall be less than or equal to the current rating of the diversion load charge controller. The voltage rating of the diversion load shall be greater than the maximum energy storage system voltage. The power rating of the diversion load shall be at least 150% of the power rating of the charging source. So what it is there is it just is what it says. It's pretty simple, pretty straightforward, but you just have some rules that you need to follow, and these are oversizing things for safety reasons. Now, we also need to comply with number 2, the conductor ampacity and rating of the overcurrent device for this circuit shall be at least 150% of the maximum current rating of the diversion charge controller. So once again, we are oversizing things. Now, we're talking about an interactive inverter being a diversion charge controller in 706.33B3. So we're using interactive inverters. And so if you have a grid-type battery backup system, once the battery is charged, you can use your grid as a diversion load. So you can send electricity back to the grid. And so if you are using the grid, you don't have to comply with 706.33B2, which we just talked about. So that's all this oversizing of wires and voltage and all that kind of stuff. And then also in 706.33B3B, it says these systems shall have a second independent means of controlling the energy storage system charging process for use when the alternate system is not available or when the primary charge control fails or is disabled. So kind of like what we were talking about up here, we're not the sole means of regulating charge. So if something breaks, we still have to be able to regulate the charge, or when the grid goes down, we still have to be able to regulate the charge. Now we are done with diversion charge controller, and we've moved on to 706.33C charge controllers and DC to DC converters. And a lot of times a charge controller is kind of a DC to DC converter. The definitions cross over. A lot of times what's happening is you have a PV array and we are changing that array voltage to the battery voltage, converting one DC voltage to another. Is that a charge controller or a DC to DC converter or both? Where charge controllers and other DC to DC power converters that increase or decrease the output current or output voltage with respect to the input current or input voltage are installed, all of the following shall apply. So then we're going to 706.33c1. The ampacity of the conductors in the output circuits shall be based on the maximum rated continuous output current of the charge controller or converter for the selected output voltage range. So we're saying we're going to base our current based on the maximum rated continuous output current. Pretty obvious right there. Our current is our continuous current. The voltage rating of the output circuit shall be based on the maximum voltage output of the charge controller or converter for the selected output voltage range. Do we even have to say that? It's just kind of obvious. The maximum voltage is the voltage. The maximum rated continuous current is the current. You almost don't have to read this, but they do take some simple concepts and then they turn this into NEC language, which makes it sound a little bit more confusing. Okay, on to the flow of part 4 of Article 706, Energy Storage Systems, which is flow battery energy storage systems. And so we are not going to Article 480 for sure with flow batteries. And let's see what else we're going to refer to, which is hint Article 692. All electrical connections to and from the system components shall be in accordance with the provisions of Article 692. Guess what that is? Fuel cells. So a flow battery is sort of like a fuel cell. So we're going to take our flow batteries and treat them like fuel cells. And fuel cell systems is Article 692. Remember the different types of flow batteries that we're talking about? And the main type of flow battery that you might ever see is called vanadium or vanadium redox. That's a flow battery with storage containers and all that kind of stuff. Usually not going to be something on a house, except we did see one that was on a house. So they do have one small one out there, but usually they're larger. Okay, the electrolyte classifications shall be identified by name and chemical composition. We're going to put that on a sign to every location in the system where electrolyte can be put into or taken out of the system. So you might have your vanadium sign there. Because we're saying vanadium because that's the main type of flow battery that we have that we're dealing with most of the time. And one of the reasons why is because it lasts for a long time because you have electrolyte that is just different states of vanadium on both sides. So you're not going to get cross-contamination, and this stuff will last for a long time. Electrolyte containment. So you got to look out for spills of electrolyte, and you will have, it says, an alarm system shall be provided to signal an electrolyte leak from the system. And also your wiring should be routed in a way that mitigates potential for exposure of your wires to these electrolytes. So yeah, you don't want to dip your wires in electrolytes. Not a good thing. Flow controls. So we're pumping electrolytes. We have pumps. It's a battery with pumps. Controls shall be provided to safely shut down the system in the event of electrolyte blockage. So if there's something that's getting blocked up, you need to turn those pumps off. Then it says pumps and other fluid handling equipment. Pumps and other fluid handling equipment are to be rated and specified suitable for exposure to electrolytes. So you're not going to just go get a water pump. You need a special pump that is rated to work with vanadium or whatever your electrolyte is. Okay, there we went from flow batteries, and we are almost at the end. And pretty much what the end here is part 6, other energy storage technologies. And so we're leaving it open for other energy storage technologies that we talked about in this course already. And so we can use other energy storage technologies. So we're leaving that door open. So some of these other energy storage technologies could be found in 706.2 definitions. We have energy storage systems, and it says in this informational note, not limited to batteries, but can be capacitors or kinetic energy devices such as flywheels and compressed air. So we didn't go into detail about these other systems, but there they are. So we're talking about things such as flywheels or capacitors or compressed air, and we're leaving the door open in case you invented some other kind of energy storage system. Maybe it's gravity power, or maybe it's dark matter. Just kidding. Maybe in the far future. Dilithium crystals. How about that, Star Trek fans? Okay, all electrical connections to and from the system and system components shall be in accordance with applicable provisions of this code. Like how they capitalize code in the National Electrical Code, because they think they are important. Unless otherwise directed by this article, other energy storage technologies shall comply with provisions of Part 3 of Article 705. And that takes us to the end of Article 706. Hope you enjoyed the show. Thanks for listening to Sean White's Solar and Energy Storage Podcast. To learn more about energy storage, go to Solar, SEAN. That's SolarSean.com.